This is the conservation of momentum practice packet solution to question number 3. The question involves a large asteroid. It's 500 kilograms, moving to the right with a speed of 20 meters per second, collides inelastically with a space rock, smaller, it's half the size, with a mass of 250 kilograms, moving to the right at 10. So it essentially catches up to it and collides. They want to know the final velocity with which they move. This is an inelastic collision, and so it will be solved via conservation of momentum principles. We'll start the problem by stating the conservation of momentum principle, the sum of the different momenta in the system before this collision occurs. When you add them all up together, must be equal to the sum of the different momenta in the system after the collision occurs. This statement right here is, by definition, conservation of momentum. And we'll basically then continue this by looking at each specific piece in the system. We've got space rock A, asteroid A, which I'll call P sub A, the momentum of that asteroid, and P sub B, the momentum of the space rock, the smaller one labeled as B. And when they hit and stick together inelastically, we'll say that the sum of the momenta after the collision is going to be PA prime plus PB prime. At this point, before the collision and after the collision, everything and all objects were moving, so I can't eliminate any of these terms, but it's prudent to go ahead and separate each one of them into their constituent parts. MAVA plus MBVB is equal to MAVA prime plus MBVB prime. So these two things have hit, they've stuck together. Of course, we know this next step, VA prime and VB prime must be equal to each other since the collision is inelastic. These two things are moving together, so therefore we're going to convert both of those instances to VF. The final velocity. Again, the only reason that I'm doing this is to narrow the number of variables in this problem that I don't know. Right now there are too many things I don't know, VA prime and VB prime, and so by kind of combining those two, since they are the same, I shouldn't be using different variables to describe the same number. So the left-hand side of this equation does not change. I still have MAVA plus MBVB. You know, solving these types of problems in some ways just involves good record keeping, kind of keeping track of things. I am going to factor out a VF over here on the right-hand side. That's ultimately what I'm trying to chase down. So I've kept it in red. I've got MA plus MB, so I've factored out the VF. On the left-hand side, I still have everything that I've had since I kind of started this problem. MAVA plus MBVB. Now I'm ready to divide both sides by this term MA plus MB, and so I'll be left with an expression for VF. VF is equal to everything over here, MAVA plus MBVB, all of this is before the collision, divided by MA plus MB. Now that I have this, the last thing that I have to do is basically just plug some numbers in for each one of these terms. The mass of the asteroid, or MA, is 500 kilograms. And I'm going to be multiplying that by the velocity that it has, which is initially 20 meters per second. Notice that this is to the right, so by convention, I'll keep that positive. And I'm going to add to it the mass of the space rock, which is 250 kilograms. And I need to multiply that by the velocity of the space rock, which is also in the positive direction, but a smaller magnitude, 10 meters per second. And I need to divide that by the sum of the two, 750 kilograms. Is going to be the sum of the asteroid and the space rock. And all of that, of course, is equal to V sub F, the final velocity of the combination of the A and B after the collision. When I run that through my calculator, I get 16.67 meters per second being the final velocity of these combined two after they collide inelastically. Oops. I was trying to draw a box around that, but it's not going to work. So why don't I just do it in pen? And there's our answer.